So at this point, in note 16, which is just like, it's the longest notes I think of the entire year. So far we made it through page 1. That one's all done. We made it through a little bit of the homework that goes with it. I'm actually gonna do some of this with you, so hold on to that. And let's start there, but we pretty much not touched any of the other pages. So let's look at homework 16 because there's a couple of problems for solution stoichiometry. I want us to kind of remember how we use molarity in a calculation. I'm going to do it on scratch paper, but you can do it in your notes. So really quick, struggle for 1 minute on your own. Try and not peek as I'm doing it as well. Balance this and see how far you can get on number 6. Okay, so 6, 2, 2, 3, that works. And the molar mass is, let's get this paper up. How many grams of aluminum are required to react with 42 milliliters? Okay, 42 milliliters, 4 molar HCl. So convert 42 milliliters into that many liters, and 4.0 molar is the same thing as writing 4 moles per 1 liter. So I'm going to use these to start out. Okay, so how many? Okay, so I have 42 liters of hydrochloric acid. Liters on top means liters on bottom. Hey, would you look at that? 4 molar. Again, this is still the HCl we're working with. Trying to figure out how much of the HCl is going to react with the aluminum. So that's my middle chunk. I've got to switch from moles of HCl to moles of aluminum. Two moles of aluminum go with 6 moles of HCl. This whole chunk came from this right here. This was the balancing in the equation. And I'm trying to figure out how many grams of aluminum. So oops, don't want to slide that. 1 mole of aluminum weighs, let me check my periodic table. I think it weighs 26.98. That's pretty good. Point 042 times 4 times 2 times 26.98 divided by the 6 in the denominator is 1.5. I'm just going to leave that rounded grams of aluminum. So I need to scoop out 1.5 grams of aluminum in order to sufficiently react with the 42 milliliters of hydrochloric acid. Honestly, the tricky part is just remembering that big M can separate into a chunklet. So trying the next one, I'll leave this up for a second if you want a picture. Pause the video. how many milliliters of lead nitrate are required to react with 87 milliliters of 0.21 molar sodium iodide? So pause the video, try this one. All right, this is a little different. Maybe you made it to this point. That's where I got. I was about to ask Alexa how much this was, but I didn't. So what she thinks I'm asking. No, I'm not asking you. Okay. I was gonna ask for the molar mass of this, but I don't actually need mass at the end of it. It's asking how many milliliters. So I need to use this concentration here, because this can be rewritten. 0.13 big M is the same thing as 0.13 moles over 1 liter. And see, I already kind of messed up here. I gotta fix this. I'm gonna put this as a parentheses here. So 0.13 moles over 1 liter. This is going to get me my answer in liters, and then I'll just convert it to milliliters. .087 times 0.21 divided by 2 and 0.13 in the denominator. So I'm getting 0.070. This is how many liters it would be of the PbNO3(2), or the lead nitrate, if you will. And then a quick conversion, there's 1,000 milliliters in a liter, so move the decimal 3 times. There'd be 70 milliliters. 70 milliliters of this is required to react with 87 milliliters of this. So there's a little bit of homework help on this one. So if you're feeling good about this, I'm very proud of you. If you're not feeling good about it, I just watch this video again or email me if you're having issues. But really the hardest part is just taking the M and expanding it. M and expanding it. In that case, we need it to flip. This solution stoichiometry problems only work like this when you have, you can only use stoichiometry when you have something that reacts to completion. So we used stoichiometry last year when we were assuming that the reaction completed in one direction, it just did the reaction. The reaction in this case, let me switch it back to the camera. The reaction that we're working with in this section is dissolving. So we're assuming that for us to be able to do the solution stoichiometry, that all of these substances were 100% dissolved. Sodium chloride, solid, completely turns into aqueous sodium and chlorine ions. This is a dissolution reaction. It is there we go. Dissolution reaction. It means it's dissolving. We're going to talk about now, we're going to switch gears. What if we're dealing with one of those substances that partially dissolves or doesn't dissolve at all, and it makes it much more complicated, as you can imagine. Now, the reason that I knew that on this problem, I knew I could do stoichiometry with the chunklets for two reasons. Reason number one, it literally had the title solution stoichiometry, so I was like, yay, I'm using chunklets. But if it didn't say that, if there was no title and it just had the problem, how many grams of aluminum are required to react with blah, blah, blah. For this one down here, how many milliliters of blah, blah, blah. I would need to know if everything in this case, like, are all of these things soluble? And the rules from the previous set of notes, the only two rules that you had to memorize, where were they? Right here. All nitrate salts are soluble. All salts containing 1+ ions are soluble. So I'm checking, is this soluble? Well, it has a nitrate, lead nitrate. Yep, soluble. What was the other one we were working with? The NaI. Na is a 1+ ion. So yes, that should also be check mark, soluble. Other substances might not be soluble, and it's going to get more complicated. So there's my intro into, I really like this section, but it does get a little bit tricky. So put homework 16 to the side now and pull out your notes, and we're going to skip a page. Page 1 is done. Page 2 looks like this with the light bulbs on it. Not going to do that yet. So put that somewhere else. And the one that I'm going to start with is this one here. So where it has the V at the top, precipitation reactions. So sometimes salts simply do not, sometimes things just don't dissolve in water. Cool. So what's really awesome is, what if we take something that does dissolve, another something that also dissolves. So I have a solution and a solution, and they're like clear. And then I mix them together and they react in a way that makes it so then they don't dissolve anymore. That'd be really cool, right? It actually is. Let me show you some videos. Let's see. Screen share. Share screen. Yes. Don't share sound. I don't need sound. Okay, so here is let's do this one. It's a pretty good intro. So he shows at the beginning, he's got no, let's see, he just got done explaining what they were. One has potassium iodide. Okay, let's read the little subtitle here. So lead 2 nitrate and potassium iodide. Cool. Okay, so here we go. He's got the lead nitrate, the potassium iodide, mixy. He's got to make them dissolve. Lead nitrate, we know it will dissolve because the rule says nitrate, oopsies, need to pause that. Nitrate salts always dissolve. And then potassium iodide, potassium is a 1+ ion, so we expect that it also is going to dissolve. There he goes, mixy. I don't know why he's mixing it that way. There we go, that's how you should mix it. Yeah, that's the point of the triangle shape. Okay, so they're very clear, looking good, and I think you just keep stirring them for a bit. Stir. Yep. That's great. Talkie. Get to the mixy. There we go. Play. So now we're putting these together. Whoa, I wish that he did that slower, but luckily this is YouTube. I can just make the playback speed like really slow. Play. No, play. Yes, play. Woo. Watch how cool this is. Dissolved up top, dissolved in bottom, splash. And now it's made this solid, a wet solid, but a solid nonetheless. That is not the same as before. We can't see through that. That is, nope. It looks so cool. And there it is at the end. It looks like you could stick your finger in there and like scrape it and get a bunch on your finger. And you could because it's a solid. That's fancy. Okay, so let's watch one more video. This is the video of the same, oopsies, I didn't share my screen. Let's try that again. Screen share, this one, share. This is the same reaction. It is lead 2 nitrate with the potassium iodide. So there's the one solution. Lead 2 nitrate solution is added. And you can see how the solid, go back. Okay, or don't. Here's the reaction. We've got the potassium iodide, the lead nitrate, and when they come together, they make PbI2 and KNO3. We're going to talk more about how you recognize that which reactions do this and which ones don't. But look how pretty it looks like. It looks like golden rain. Someone should make like a precipitation reaction. That's what these are called. Someone should do a precipitation reaction ASMR video. Maybe like, today we're going to take lead to nitrate solution. And I don't know. It'd be really cool though. I'd watch that. And here it's showing the same exact reaction, but instead of them mixing together in a beaker, they're just kind of showing in a petri dish how it occurs on the boundary where the two of them have connected with each other. It's really cool. And the rest of the video is just repeat. So pretty though, so pretty. Okay, close this, close that, minimize this, too many windows on the thing. And switching you back to this. So what we're looking at is precipitation reactions. Precipitation means rain, and it makes sense that like why they would call this a precipitation reaction, because it looks like it's raining stuff from the sky, just boop, and it all falls down. So a precipitation reaction occurs if two aqueous solutions are mixed together, and when they do, an insoluble solid forms. So let's see. We'll do the one that was on the video. These are some real life pictures of what they look like. And this is one that I got from an AP test a couple years ago. This is how the AP illustrators that draw stuff, this is how they show a reaction. And I got to zoom in a lot, and you got to look at your paper very closely. Do you see how they're showing? Like you can kind of see there's like a little, I don't know if I can do this, it's so tiny. There's like a little S shape in there and stuff. They're trying to show that it's precipitating. So this is the AP version. It would be printed a little bit more clearly on the AP exam, but that's what they're trying to show. This is the cartoon version of the real live version over there. Keywords might include something like cloud, like when this drips into this, it becomes cloudy. And you're like, oh, okay, they're trying to describe a precipitation reaction. Wow, that's blurry. Sorry, my bad. There's your keyword. Cloudy, stuff like that. So here's an example of a potential precipitation reaction. We have Ag, that's silver, NO3 nitrate. We have silver nitrate, which is soluble. The AQ there is telling us that this dissolved. Silver nitrate, that makes sense because all nitrate salts are soluble. And sodium chloride dissolved, which makes sense because sodium is a 1+ ion and those are soluble as well. So both of these are dissolved. And we're trying to see when they mix together, do they form something that does not dissolve anymore? So we're going to switch partners of the reactant pairs to determine the formula of the products. AgNO3 broke up into Ag plus, NO3 minus. The NaCl broke into Na plus, Cl minus. We got to figure out how do these come together. I can't put Ag plus and Na plus together. Two positive charges? No, that's not happening. Two negative charges? No. So we have to do like a swappy swap. And we're going to put the silver positive with the chlorine negative. We're going to put these together. So AgNO3. And we decided that AgNO3 was aqueous because like we already did that. You can either write it like this, or you can write it out separate. Either way you like, but for saving paper, I'm gonna do this one. Oh, Archie's barking at something. Let's go take care of it. NaCl aqueous. These are what was combined. Archie boy, come here. And then doing the swap, like we identified here, that's going to make Ag with Cl. And we don't know if that's soluble or not. So I'm just going to put the parentheses, but I'm not going to write anything in it. And Na with the nitrate. So I check my rules, right? All nitrate things are soluble. So I'm like, yep, sodium nitrate, aqueous, goes into the aqua, it dissolves. And the silver chloride, I'm kind of like suspicious of, because like, yeah, Ag plus, like it did end up being +1, except for like, it's not in the +1, +2 column. And it turns out it actually like doesn't dissolve. So I'm going to put a solid, S for solid there. So this is a precipitation reaction because we have aqueous turning into something solid. Generally, this one is a little bit tricky because you're like, but wait, it's +1 and it says right here. Yes, but it's not in the +1 column. So we're gonna like not worry about that one. But let's do some other ones that are a little bit easier to see. Again, there's a couple different ways to write the reaction. If you prefer writing it like this, where it's together, Na2CO3 aqueous. Okay, that's meaning that this is able to split apart into aqueous ions. Let me zoom in. You can either write it together with AQ, you can write them separately as ions with the charges. Same thing here, calcium nitrate is aqueous because nitrates are always soluble. So here it is breaking up into the calcium and the two nitrates, both aqueous. I don't really like writing it this way below. This is called the complete ionic equation, and it represents everything as ions like that break apart. I don't really like it because it seems to just take up like how much more room this takes up, but it does end up being helpful for the third step. This plus this made this, and apparently calcium carbonate is a solid. There's no way to write that out. It just is. This is the molecular equation. It kind of keeps them together as molecules. This is the complete ionic equation. It separates them out into ions as much as possible, but we couldn't do that for the solid because it's not aqueous. And then the net ionic equation is where we say, okay, what actually made that solid? Because that's the cool part. Nobody cares that there were 2 NAs that went in and 2 NAs that went out. I could literally just like, you did nothing. You did nothing. And also these nitrates did nothing. They just went in and came out. So the net ionic equation is like, what actually happened, this and this came together to make this. If you'd like, you can use that middle step, but in my head, it's pretty easy to see how did calcium carbonate form? Oh, well, we must have had a calcium ion mix with a carbonate ion to make it. I can see that, but also I've been doing this for a bunch of years. So if you need that middle step, that's fine. And sometimes the AP test will say, write this equation out molecularly. Sometimes it'll say, write out the complete ionic equation. But more often than not, this is usually the one that the AP test will ask for, is the net ionic equation. Write the net ionic equation showing the formation of calcium carbonate solid. Bam. Okay. Now, this is where it gets tricky. If you've been like half listening, half paying attention, on your phone texting, cool. Don't do that anymore because this is a really hard section, and just fair warning. I like it a lot. A lot of students, once they figure it out, they like it a lot, but it's very frustrating until that light bulb turns on. I was gonna turn on a light bulb over here. Light bulb turns on, but it can also be really frustrating until then. So just be sure to pay attention. So back to the notes here. This is new stuff that you've probably never seen before. We're dealing with equilibrium, and specifically equilibrium related to solubility and dissolving. So in honors chem, we dealt with some equilibrium. I said equilibrium is like a K value, and if you're taking the equilibrium of an acid, then it's Ka, which is true. This is the equilibrium of an acid. We're going to start out with taking the equilibrium of something that is soluble, and we're going to do SP, talk about that later, but KSP is a solubility equilibrium. Now, what does that even freaking mean? It means this. The fine print says that soluble is, I don't know, depends on your textbook, but generally you have to get a couple of grams into 100 grams of water. You've got to be able to get a certain amount of powder to dissolve into the water. But what if you get a little bit to dissolve, but not quite the threshold amount? On the one hand, some students will say, well, it's insoluble, it didn't cross the threshold. But like I would say, a good bit of it actually did dissolve. Insoluble, it's not really an absolute term. So we're going to go with slightly soluble. Slightly soluble salts, that's a tongue twister. Slightly soluble salts establish. Slightly soluble salts establish an equilibrium between being dissolved and undissolved. Okay. When the solid is first added to the water, no ions are initially present in the water. That makes sense. When we put, I don't know, salt, a solid, into a beaker of water, it begins to dissolve. There's nothing up here in the water, and we have to wait for this to dissolve up before there's going to be anything in the water. As it dissolves, now look, we've got stuff. as the dissolution proceeds, as the dissolving proceeds, the concentration of the ions increases until equilibrium is established. So the salt is continuing to dissolve up, but what happens with slightly soluble stuff is that, looky here, whoop, this one changed back. Equilibrium is all about the back and forth. That's why I got it tattooed on my arm. Whoops, you can't really see it from that angle, but right, here's my equilibrium arrow. I don't even know how to get this on the camera. We've got the forward, we've got the backward. If it's dissolving one way, it's undissolving the other way. Dissolving, re-solidifying. I liked that idea so much, I got it tattooed on my arm. So on the one hand, things are dissolving and re-solidifying. At the beginning of the dissolving process, there are more arrows dissolving and not as many that are re-solidifying. But once they become equal, see how we've got 2 of them going back and 2 of them going forward. Once we get to that place, this is called equilibrium, when the same rate is happening. Remember that the equilibrium sign looks like this: forward and backwards. And that's what I've got on my arm. And then everyone's like, wait, no, it's not. It is, see, equilibrium. But my my tattoo artist convinced me that instead of just having it cut off here and here, that I should get it banded around, because eventually I'd like to have a sleeve of like science stuff up my arm. So this is kind of the cutoff of like no more tattoos past this point and then up here. So I ended up getting it put into a band. So that's what it is. That's my tattoo. So on the one hand, when we're going forward, the forward arrow is dissolving. And the backwards arrow in this case is undissolving. I'm going to say re-solidifying. And that's the equilibrium that we're working with. So writing out an equilibrium, let me get a scratch paper so I can draw you something. In Honors Chem, this is how I describe equilibrium. And even though this is my scratch paper, I would do this in your binder. Like, just pull out a piece of paper, decide if you want it after you've already written it, but it might be helpful for you. So here's how I think of equilibrium. There's 2 piles of sand. And there's little ants. I don't know how to draw ants. There we go. Ant number 1, ant number 2. I probably should have like 3 pieces and like a thorax or like an abdomen or so. I don't even know. But I've got these 2 ants. And every day, this ant wanders over here, grabs a grabs a grain of sand from this pile and walks it back. The other ant is doing the exact same thing. So this guy goes over here, grabs a piece of sand, puts it in his pile. And this ant is going over there, grabbing a piece of sand and bringing it back. all day long, they're doing this at exactly the same pace. They're ants, they go the same speed. So I don't know, maybe at the beginning of the day, this guy had orange sand and this one had blue sand. I come back and check on them and maybe their piles are a little bit, you know, maybe there's some more blues in here and maybe there's some more yellows and or oranges in this one. They've mixed the piles because they're going whoop, 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 and they're transferring, but the pile size wouldn't change, right? If they were converting back and forth at the same rate, the pile sizes wouldn't change. We can use the pile sizes as a ratio to determine when we reach equilibrium. Keep that paper, we'll use it later. So when we're doing an expression, we're going to take products over reactants in a ratio, and that equals K. So if on my little thing here, if this was my reactants, and this is my products, my expression would be K equals concentration of products over concentration of reactants. Always, 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 always. You can memorize that. K equals products over reactants. And in this case, I don't know. If I were to look, this pile's kind of tiny. It looks like maybe it only has 150 grains of sand in it. I don't know. Products over reactants. That one looks like it's got a lot more. If this is 150, maybe this one's like 500-ish. 150 over 500, just as an example, equals 0.3. For our picture, we know that the system is in equilibrium when K equals 0.3. But Ms. Oliver, how is that system in equilibrium? Because the piles aren't even equal sizes. No, they're not. That's the point. Equilibrium is not equal sized piles. It's equal rates. Equal rates back and forth. Equal rates back and forth. Same number of arrows one way as the other way. Same number of arrows one way as the other way. It's not about the size of the piles. It's about the rate. So let's do it for some real examples here. I don't like using conceptual examples for too long because then we don't actually get any real science done. But here's a reaction. Calcium phosphate solid equilibrium with 3 calciums and 2 phosphates. Aqueous, aqueous. This is showing a dissolution reaction. It's a reaction that's showing how its solid form dissolved, just broke apart. the equilibrium expression is always, 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 here's your template always, K equals concentration of, I'm sorry, I turned my paper, products over reactants. Always, 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 always. So if I'm trying to write the K for this reaction, I'd say these are my products, products, whoop. I've got it here. There's one of them. Here's the other one. Over reactants, over, the reactant was Ca3PO4 2, but there is one rule. You need to delete solids and liquids. So that's why this actually isn't written in the denominator. The 3 and the 2 go here and here. So let's do some examples. I'll do some more. It's really not hard at all. Let me do that same one, but writing it out myself. Calcium 3 phosphate solid breaks apart into 3 calcium 2 plus aqueous and 2 PO4 3 minus aqueous. K equals products over reactants. These are my products. 1, 2, they're going to go up top. Reactants are going to go underneath. So far, what I have is calcium, and the 3 in the front becomes the exponent. My other one, phosphate. The 2 becomes the exponent. Products over reactants was calcium 3 PO4 2. Last step, remove anything that is solid. So my final answer for this, K equals Ca2 plus to the third power, PO4 3 minus to the second power. That is the expression that I will use for this reaction when it's in equilibrium. So here, write the equilibrium expression for the following. BaSO4 solid, BaSO4 solid. That would be breaking apart into barium 2 plus ion and SO4 2 minus ion. I would get, for one of these, I get one of those and one of those. Products over reactants. Each would be raised to the 1 power, but I don't want to write that because that's redundant. Products over reactants, but wait, that's a solid, so I'm not going to write it. K equals this. CaF2 solid. Solid, I forgot the S. It's going to break apart into that 1 calcium, 2 fluorine minuses, products. And that 2, that 2 in the front makes that squared. Products over reactants, but that's a solid, so I didn't need to write it. That's what K equals. This is the expression that we will use when determining the equilibrium of this reaction. Now, this was conceptual. This is the expression, but all of this is going to switch to mathematical like it always does. Up here, you could probably find the ones that we just did almost exactly. Let's see. We either can find barium sulfate, calcium fluoride, or calcium phosphate. Let's see if I can find any of those here. Here's calcium sulfate. Oh, no, that wasn't one of them. Sorry, let's look. Calcium phosphate. Here's the one right here. Here's the one right here from this. Calcium phosphate. Wham bam. Calcium phosphate. Calcium phosphate. And we wrote that the calcium phosphate expression was that it was calcium to the third, phosphate to the second. And this number here, 2.0 times 10 to the negative 29, that's where you're going to plug in for K. K is a number. Just like with those ant piles that we did, we were able to calculate K is ultimately a number that represents the expression. Whoa, I hate it and love it at the same time. It's so complicated. So let's look and see if we've got barium sulfate on here. Barium sulfate, okay. So barium sulfate, let's see if I can cover. I don't know how to do this. I don't know how to get everything on the projector that I need on the projector. Please stand by. All right, barium sulfate, BaSO4, that's the one we had right here, barium sulfate. Our expression was Ba2 plus times SO4 2 minus equals K. K equals 1.1 times 10, gosh, what does that say? To the negative 10, I think it says. Cool. What would it be for calcium fluoride? Calcium fluoride, CaF2. This was my expression, and that equals 3.9 times 10 to the negative 11. This is the value of K. This is the K expression. So maybe make note of that on your paper, that over here, this is the value of K, but when it asks for the expression, you're putting it together like these. Now looking at the full page, look through all of your stuff, look through all of your papers. I printed you a much higher quality of a KSP chart. Just kidding, I looked through the packet, I didn't. This is as good as it gets. But I can print this for you in a little bit higher quality so that way it's easier to read. But to be honest, most of the problems that you will encounter, you don't need a table because they will already give you the information that you need in the problem itself. So like down here, these two examples, lead 2 chloride dissolves to a slight extent in water. A sample is left to dissolve in water and has dissolved as much as it's going to, aka it has achieved equilibrium. The probe found that the lead ion concentration in the beaker was this. Use this data to show how they determined the KSP in the table above. So this problem, we're going to use the data to figure out how in the world did they figure out that lead 2 chloride is 1.7 times 10 to the 5th. This example shows how they made this table. They took each of these compounds, left them in water, came back after it had achieved equilibrium, probed it, and then did some maths. So let's show how to do it. Lead 2 chloride is this one, Pb, Cl2, because it's lead 2 plus. Chloride is in the 1 minus always column, so we've got to put them together like this. Pb, Cl2. In equilibrium, you get 1 Pb and 2 chlorines. This is our reaction. This is a solid. The ions are aqueous. Always put the solid on the left. These are dissolution reactions. They're showing how something dissolves. So you want to start with the solid in order to show how it dissolves. So my equilibrium expression would be products over reactants. Products over, let's see, I still got products. That exponent 2. Products over reactants. I'm going to write it anyway, even though I know I'm just going to cross it out because this is a solid. But nope, solids don't exist. Products over reactants. And somehow they were able to figure out that this is what K equals. How'd they do that? Well, if K equals Pb 2 plus and Cl minus squared together, look at the data. The lead ion concentration was this. So I'm going to plug that in right here. because brackets mean molarity. So I'm going to plug that in here. And if that's the lead concentration, we have twice as much chlorine. So not only are we going to square it because the formula said to, but we have twice as much of the chlorine. So I don't know what that is. 1.62 times 10 to the negative second times 2. So 0.0324 is what's going in here. It is twice as much, and it's getting squared. It's getting squared because the formula says so, but it's twice as much because every time that this breaks apart, we get 2 of the chlorines. So now let me punch this in the calculator. K equals 1.62 times 10 to the negative second times 0.0324 squared equals 1.7 times 10 to the negative fifth. Is that what matches the chart? Yay! So this is how they figured out all of the values in this table. They took the compound, let it sit in water until it was done equilibrizing, measured the concentrations, and put it together in a nifty table. Well, that's fine and dandy, Miss Oliver, but why do I even need all of this data? Oh yeah, because you can't do any of the problems without it. You can't do any of the problems without it. So again, the number in the table, the value is the fraction that corresponds to when the system is in equilibrium. Everything that we're going to be dealing with in AP Chem from pretty much here on forward is a system in equilibrium. It'll either be an acid that is losing its hydrogen, regaining its hydrogen, that's an equilibrium. We'll be dealing with a solid that's dissolving, but that can also resolidify. That's why AP Chem is so much harder than Honors Chem. Honors Chem, you've got the arrow going one way. AP Chem, now it goes the other way. So we need to have the value associated with the equilibrium when it's going back and forth. So finishing out the page, the KSP value of copper 2 iodide, not listed in the table, I had to go find it somewhere else, is this. So let's see, copper 2 iodide would be, we've got copper with a 2 plus charge. Iodide is IO3 minus 1. It's a polyatomic. So putting those together, I would have copper like that. Copper 2 iodide. KSP means we're dealing with solubility, so put the solid on the left. It's dissolving into the copper ion, aqueous, and the iodate ion, but I need to put a 2 in the front because there's twice as many. That's my dissociation. I'm going to label this really good here. So this is my dissociation reaction. Over here, I'm going to write my equilibrium expression. The expression would be K equals products over reactants so in this case, I had the copper, the iodate squared over this thing that I'll cross out because it's solid. Fine. So simplifying, this is my dissociation reaction. This is my equilibrium expression. It says the value of K is 1.4 times 10 to the negative 7. This is our value for K. It's not the expression for K, it's the actual value, but kind of same. This is like equilibrium expression, equilibrium value. And what it wants us to find is to calculate its molar solubility. Calculate the numbers for the piles because brackets mean concentration, just like over here. The products pile in brackets, I estimated from my picture, I was like, oof, not a very big pile, maybe 150. How big is this pile? 500. We're wondering the same thing. What numbers go in here to make 1.4? I'm actually not going to finish this with you. I don't think it's relevant at this point. I am going to put a sticky note. I am going to put a sticky note here so that we come back and solve it. Note to self. Finish this. So in a different video, I'll end up coming back and finishing this. But the whole point of the lesson today, this whole 3 hour long, however long it's been, is just to say we're dealing with things that dissolve. Dissolving is this arrow. AP Chem makes it complicated because things are going to undissolve. The amount of dissolving and undissolving needs to be equal. That's called equilibrium. Equilibrium, don't know why, but equilibrium is represented by the letter K. So at equilibrium, we have an expression for the reaction, and we also have a numerical value. The numerical values were figured out by actually doing experiments to get them.